Okie doke. So now we're going to look at the specified model to basically, yeah, especially since we didn't properly go through the theory of the general model, to get an idea, do some math, and get a better grip on the intuition. So let's see what's going on in this model. So what have we got? We've got Y is, so GDP or production is ALL to the 1 minus alpha, R to the alpha. So that is effective labor, Cobb-Douglas with effective labor and the resource input. And then it's knocked back by a pollution term which is less than 1. It's e to the minus pollution to the phi. So e to the minus something is always going to be less than 1, right? If the something is 0, then that's 1. There's no sort of knockback from pollution. As pollution goes up, we knock back production more and more, okay? We've got some growth in the effective inputs of labor. There's no capital. And the resource input is the sum of a series of different inputs, n inputs. And each of those inputs is linearly linked to some flow of pollution. So it's very straightforward. We can think of coal, oil, and wind. So the biggest psi would be for coal, and the next biggest would be for oil, and then wind would have 0. Okay. So what happens next? We can interpret these alternative technologies as simply alternative resource inputs, like I said, coal, oil, wind, or high sulfur coal, low sulfur coal if we're talking about sulfur. But a third technology, it could also be like some end of pipe, coal plus end of pipe cleaning, which would be more expensive, less polluting, so a lower value of psi, a higher value of W. If the input is simply a natural resource, we can think of it as being extracted competitively from a large stock, so then the price is constant, right? If we've got some end of pipe cleaning like FGD, flue gas desulfurization, then again we just assume that there's some extra fixed cost of doing that. And then we're interested in in aggregate production net of extraction costs, Z. So that's the sum of the WJ DJs over the J's. And remember that R is the sum of the DJs, so R to the alpha becomes the sum of the DJs to the alpha. So this is our sort of gross production initially. Here it gets knocked back by pollution. And here we subtract the costs. And we're left with consumption. So the social planner basically just wants to maximize this Z, right? And for now, we assume there are two technologies, 1 and 2, just for this to do some simple math. Okay. And we can take first order conditions in D1 and first order conditions in D2, or the first order condition in D1 and then again in D2. So remember, this term before the minus, that is Y, yeah. So we have alpha times Y over D1 plus D2, which is this sum, plus we've got a D1 in here as well, and the differential of e to the minus psi1 D1 minus psi2 d2 all to the phi turns out to be this. Sorry, with the psi1 as well, all times y. Shall I take you through that? No, I don't think so. I think we can talk about it in class, or you can, yeah, swat up on your differentiation. You should be able to do it. Use the chain rule. Okay. And then, of course, the first order condition in D2 is exactly symmetric to that first order condition in D1. And in the optimum, basically these two things with the left hand side and the right hand side, we can give them intuitive interpretations, because this is like the marginal benefit of using more of the input. That's the boost in the gross production y. And this is the marginal cost, which is the sum of two terms, the extraction cost W1 and the pollution damage cost, which is increasing linearly in y. So the richer we are, the more damage you get from a given unit of pollution. And interestingly, for D2, the benefit side is exactly the same, but the cost side differs, because now we have a different extraction cost and a different pollution factor. And remember, we said that, well, have we said that yet? I think we're going to say that the first input is cheap, so W1 is less than W2, but dirty, so psi1 is greater than psi2. So, what happens? So we start with this case, W1 less than W2, psi1 less than psi2. Oh, okay, so we start with a bit of an odd case. D1 is both cheaper and cleaner. Then D2 will never be used. And then initially it's like this sort of two steady states. When productivity is very low, damages are sort of negligible, and it's basically the extraction cost that dominates. The extraction cost is constant, so over time we use linearly more and more of the input, and we get linearly more and more pollution. But then in the very long run, instead, the damage cost dominates the extraction cost. The damage cost increases linearly in y, so then we've got like the price of using the resource D1 increases linearly at the same rate as the growth rate. The quantity used will be constant and pollution will be constant. So let's see what it says here. When only input D1 is used from any given initial state, P increases monotonically and approaches a limit of P bar, which is alpha over phi to the 1 over phi. And if we go backwards in time, the growth rate of P will approach G, which is the growth rate of the effective labor inputs. Okay, am I going to take you through the math of that? I guess I should. Okay, so let's just have a look at the math of that. So we've got the first order condition was alpha y over d1 plus d2 equals w1 plus phi, and then we got psi1 d1 plus psi2 d2, but that's just p, right? Psi p to the phi minus 1 psi1 y. Okay, and then in the limit of high inputs ALL, I guess I'm not going to go through this super rigorously, but we can basically see that y is going to approach infinity, so y will dominate w1. So in the limit we can ignore w1 and we can write alpha y over d1 plus over d1. There is no d2 in this setup right now. We're assuming there's only one input. Is phi p to the phi minus 1 psi 1 y, but then those y's are going to go out, right? So we have alpha over phi equals d1 p to the phi over p psi 1. But if we go here, let's see, psi 1 d1 is just p, so psi 1 d1 and p go out, so p to the phi is alpha over phi, p is alpha over phi to the 1 over phi. So that's super straightforward, that in the very long run pollution approaches that limit. If we go backwards in time and let net inputs or effective labor inputs go to 0, then y goes to 0. And again, if we zoom in on this, then this term becomes negligible compared to this, which is just constant. Pollution damages are negligible compared to the cost of extraction. So then we have alpha y over d1 equals w1. So alpha y is w1, d1, alpha and w1 are constant, so y and d1 grow at equal rates, which is going to be at the growth rate of effective labor, G. Okie doke. Okay, so that's the case with only one input. And I've talked you through all of that. Yeah, because of course in between those two extremes we have this transition, right? I've talked you through all that text, and I should stop the video here and then we'll look at the case with two inputs.